Hello, everyone. We are back with another episode of Computer Vision Talks after a very long break. And today we have with us Nikhil. Interestingly, Nikhil has been one of the people responsible for running Computer Vision Talks in so long. Earlier as a regular participant, and today as a host and making things run smoothly. Apart from that, Nikhil is also a PhD student at University of Queensland and IIT Delhi's Research Academy. His research focuses on incorporating geometric priors into urban scene understanding. And today we are going to discuss a paper by Nikhil, which was accepted at ECCV 2022. And this one is especially close to me because I am working on a similar kind of a research problem, which is a mix of domain generalization, adapting to different domains without a degradation in performance. Am I right, Nikhil? Over to you. You can start.
Yeah. Thanks, Shambhavi. Thanks for the kind introduction. It's a pleasure to be in Computer Vision Talks, being as an organizer as well as being a presenter. So today I'll be presenting my work, Master of All Simultaneous Generalization of Urban Scene Segmentation to All Adverse Weather Conditions. So this work has been accepted at ECCV 2022. This is a joint collaboration with Abhinav Singhal, Abhishek Kumar, Professor Mahasa, and Professor Chetan. So let's get started. So the problem statement which we are focusing on is semantic understanding of urban scenes, where for each pixel we need to classify which class it belongs to. So for example, in this case, we have red class for person, blue class for car, and pink class for footpath. So for safe and reliable AI, we need to accurately predict where the boundaries of different classes are. So that is our current problem statement. So however, the current AI techniques perform well in daytime scenario. We can see in the above scenario where we have clearer daytime weather condition. The performance is very accurate. But as we go through adverse illumination conditions such as night, the performance start degrading even for state-of-the-art techniques. So our goal is to improve generalization performance for adverse weather and illumination conditions. So the goal of current work is to out-of-domain generalization. It plays a pivotal role in the success of deep neural networks in real-world applications. So this problem fundamentally arises due to an issue called domain shift, where the training domain and test domain have different data distributions. So this domain shift can happen due to multiple factors such as input corruption, adverse weather, such as rain, snow, etc., and illumination changes such as night. And it can happen due to adversarial attacks and sensor malfunction. Ensuring robust performance under this domain shift is critical for the real-world applicability of deep neural networks. So the task which we are doing it is called urban scene semantic segmentation. So just to formalize the problem statement, given any model which is trained on source data, which is daytime condition, our goal is to perform well in different weather and illumination conditions, such as fog, rain, snow, night, cloudy, and overcast conditions. So for real world applicability, it's very critical to perform well in all weather conditions. So that's our problem statement. So let's compare the different techniques available in the domain adaptation and domain generalization literature and see where the current problem fits in. So in the literature, we have unsupervised domain adaptation techniques, where we have a labeled source domain and we have unlabeled target data. So the goal is to improve the performance on unlabeled target data by using labeled source model and labeled source data. And we have a setting called as domain generalization, so which aims to perform well on unseen target data without having access to the unseen target data during training. So if you see the problem setting in unsupervised domain adaptation, we have access to source data, source model, and we have access to unlabeled data. So we don't have multiple targets during unsupervised domain adaptation, and there are no open targets in unsupervised domain adaptation. So there is a paradigm called source-free domain adaptation, where we don't have access to the source data. We just have access to the source model and unlabeled target. And there are no multiple targets and open targets. And third setting is called open compound domain adaptation. This is from CVPR 2021. We have access to the source data, we have access to the source model, and we have unlabeled target during training. And we can have multiple targets as well in target or test domain. And all the targets are treated as open targets. And the fourth setting is domain generalization, where we have access to the source data, source model, but we don't have access to the unlabeled target during training. And there are no multiple targets, and every target is treated as an open target. So in the fifth setting is where the current problem fits in. That is the test time adaptation. We don't have access to the source data, and we have source model, and we don't have access to unlabeled target data during training. We don't have multiple targets, and all the targets are treated as open targets. So the current problem statement fits in the setting of test time adaptation. So coming to the differences between unsupervised domain adaptation and test time adaptation. If you can observe in unsupervised test time adaptation, we have source data, which is shown as DS. We have access to XI, YI, both label and data. But whereas in target data, we don't have access to YI. And we make sure that the source model is adapted to the target data and the performance on target data is improved. But whereas in fully test time adaptation, we have the model which is trained on source data, but we assume that the source data is no longer available to us. We initialize the model and we adapt it to the target data. So the question arises like why test time adaptation is important, why access to source data is critical in case of unsupervised domain adaptation, and why it is not available during fully test time adaptation. So the main reason for this is due to data privacy issues. For example, if we consider face recognition systems, which are trained inside some private data, let's say source data in this case is private, and we don't want to leak this data to outsiders. So having access to source data is a limitation in such scenarios. So test time adaptation makes much sense due to data privacy issues that can arise due to sharing your source data. So in the fully test time adaptation can be a practical scenario in such settings, which can overcome this issue of privacy issues. So that is the difference between unsupervised domain adaptation and test time adaptation. So coming to the related work, the first method which proposed this technique is in ICLR 2021. So the work is referred as 10. So the goal of current approach is to handle the domain shift in the target data that can arise directly during inference. So what 10 does is that, let's say in training the model, we have X's and Y's. We have a model which is trained on X's and Y's. During fully test time adaptation, we have Y hat, which is the predicted label of predicted probabilities on the XT. And we use entropy as a loss to adapt the model in such setting. So more specifically, the 10 tries to adapt the affine parameters of the batch norm layer to minimize minimum entropy loss for each test sample. So 10 only adapts sample level adaptation. So the model is reset after each sample. So unlike 10, yeah.
One question on tent here, that tent adapts using the batch norm layer, right? So would it still work for a batch size of 1?
Batch norm for 1 is not, I think it throws an error. It doesn't take the input for one input. So what they do is that they do different augmentations of the same image. So they perform different augmentations of same image so that they don't get into such issue. Because to calculate mean and variance, we need at least more than one sample.
Right. Okay.
Yeah. So unlike 10, the current work is focused on improving generalization in adverse weather condition using something called as edge consistency. So we will go over it in the upcoming slides. So coming to the related work in domain generalization. So the recent work is called RobustNet. This is from CVPR 2021. The task is to improve domain generalization in semantic segmentation. So in the proposed approach, they use something called as instant selective whitening. So what they do is that they take a image xi and its corresponding photometric transformation tau of xy, and they take the intermediate feature maps representations, and they calculate the covariance matrix of xi and tau of xi, and they find the variance between both of them and suppress the high variance values. So intuitively, what they are trying to do is that they are trying to suppress the domain specific style information from the original image, thereby making the feature maps more domain invariant. So to make the feature maps more robust, they are taking the photometric transformations of the input image and trying to suppress the highly correlated values from the variance matrix. So the current work aims to complement the domain generalization approaches by directly adapting them to unseen weather conditions. So important point to note here is that domain generalization approaches assume that they don't have the access to the target data. In our current scenario, it is different weather conditions data. So our goal is to adapt these models to unseen weather conditions. So coming to the proposed approach, given an input image, we compile the batch of images and we forward pass the batch of images to the proposed to the neural network f theta, and we get the semantic segmentation predictions capital S. If you observe that the initial prediction, it doesn't have the edges corresponding to the input image. In the initial prediction, we can observe that the edge corresponding to the footpath, which is shown in the pink color, is completely missing in the initial prediction. So our goal is to improve this performance by enforcing these edges present in the input image directly onto the predictions. If you observe that in iteration 3 and iteration 5, we'll slowly start to recover the edges which are present in the input image into the predictions. Whereas in the initial prediction, we don't have this edge consistency with respect to input image and the initial predictions. So the proposed framework improves the semantic segmentation predictions by penalizing the semantic segmentation predictions if the label edges do not align with the visual edges present in the input image. So whatever the edges present in the input image should be maintained in the predictions. So that is the goal of our proposed approach. So we call it something called as edge consistency prior. So we use this edge consistency prior to enforce the consistency between visual edges and the label edges present in the predictions. So the overall idea of this proposed approach is to do multiple forward and backward passes to improve the predictions of the capital S. So the updates are done based on a loss function called a loss function L of S. So we will see in detail what is the formulation of this loss function, because the loss function is important to how the model is updated and how we are maintaining these edges. So one important point to note is that this f theta can be any pre-trained model because the loss only depends on the output predictions. So, and it can be used with any pre-trained model. So coming to the loss function is based on something called as graph cut. So I'll go in at high level how graph cuts will work. So for a input image shown in this here, it has 9 pixels. So what graph cut does is that it treats each pixel in the node in the image as node in the graph. And in this case, we have 9 pixels. So we have 9 nodes in the graph. And we create source node and the sink node, which is shown in S and T. So the goal is to group the pixels based on the similarity between how close these 2 pixels are. In this case, we can observe that this above 5 pixels are close in the color and the location. So they are grouped into the same segment. So what graph cut basically does is that it partitions the pixel based on how similar these pixels in each group are. So the similarity between 2 pixels can be defined based on multiple ways. So we will see how we define and based on the input image. So any questions still here? No, okay.
It was pretty clear.
Yeah. So the loss function we are proposing are based on normalized cut loss. So normalized cut is a popular graph partitioning algorithm, which is designed for binary image segmentation task. So normalized cut is actually proposed in the year 2002. So, but the problem with this normalized cut loss function is that it is proposed only for binary image segmentation task, and it is non-differentiable. So we make relaxations in this loss function to make it differentiable, so that it can be used in the neural network settings, because to do the backward passes, we need the loss function to be differentiable. So we will see how exactly we modified the loss function. So the notations are, let capital I be an image, capital A be the affinity matrix or similarity matrix, D is a degree vector, which is defined as A cross 1, and capital S be the segmentation predictions. So for a binary image segmentation task, the normalized cut loss for partitioning into foreground and background pixels is defined as equation number 2. This is the actual equation used in the work in 2002. However, equation 2 can be written as equation number 3. The derivation actually is in the paper, so it's not possible to, they use something called as eigenvalue approximation to come to this derivation. So due to time constraints, I'll not be able to discuss how equation T is converted to equation 3. The derivation is in the paper. So to extend it to the multi-class setting, we extend it for, we take a class specific segmentation mask SP. For each class, we would like to do the same thing, normalized cut loss for each, treating it as one versus all approach. And we propose a multi-class normalized cut loss. So here A is the affinity matrix, which is the of size number of pixels cross number of pixels. So for any 2 pixels, we define the similarity between those 2 pixels based on a 5-dimension vector. So the 5-dimension vector is defined by the RGB values and the location XY of the pixel. So for any pixel, we have a 5-dimension vector based on RGB values and XY location. So for this 5-dimension vector, we use Gaussian kernel to get the values in this affinity matrix. So if 2 pixels are having similar color and similar location, their affinity or similarity will be higher. So these are calculated based on the original image. So the affinity will give us an idea how 2 pixels are close in the image space. So basically this 5-dimension vector will give us an idea if there is a edge between 2 pixels or not. Because if there is a edge between 2 pixels, the color will suddenly change and the similarity will reduce significantly. So if the similarity between 2 pixels is reducing significantly, that means that there is a possible edge in their case. And that should be maintained in the predictions as well. If the edge consistency with respect to the affinity matrix is not reflected in the predictions, the loss value will be higher in such scenarios. So since the loss value is higher, the network will penalize and adapt the network in such a way that the edges should be preserved. Further, still the equation number 4 is non-differentiable. So to use it in a neural network setting, we propose a relaxation to the SP. SP will be the segmentation probabilities of belonging to class P. We modify SP of IJ as the probability of pixel I of AJ belonging to class P. Instead of just using 0 or 1, we modify it to be probability of belonging to a class P. So the overall loss function will become as shown in the equation number 5, where SP will be now probability values instead of 0 or 1, and we'll take the softmax of different probabilities. And there is an issue with the current existing benchmarks. This is referred as class imbalance. So most benchmark datasets have skewed ratio of minority pixels and majority pixels. For example, if we consider traffic light pixels compared to road pixels, so the road pixels are the majority pixels. They'll be in approximately very high ratio in among all the classes. But whereas the traffic light pixels are very small in number. But however, this classes, traffic light class is very important to us because it will help to make reliable decision in the real world applications. So to handle this class imbalance, which is in the benchmark datasets, so we propose a factor called as WP. So this WP will now increase the weightage of the minority classes. So we define this WP based on normalized frequency of class P. So in this case, if you observe that, let's say class P has traffic light class, the log P will be higher for that case. So WP will be higher for the traffic light class. So in the loss function for each class, we'll multiply this WP. So which is the normalized frequency of class P. So the overall loss function will be represented in the equation 7. So this loss function is used in the backpropagation of in the L of S, which is defined in the proposed approach. So the gradient backpropagation is based on this loss function. However, the equation showed in equation 7, A is very high dimension matrix. For example, if we consider an image of size 1000 cross 500, so capital A will be 5 lakh dimension cross 5 lakh dimension, because 1000 cross 500 will be 5 lakh, and capital A will be number of pixels cross number of pixels. So it will be in 5 lakh dimension space. So to compute a multiplication of SP cross A, it will become a huge computation because SP will be 1 cross 5 lakh dimension and A will be 5 lakh cross 5 lakh. So this is not feasible to multiply for each image. So what we do is that we propose a relaxation into the loss function so that it can be computed, because during inference we are computing this loss. We cannot afford to for huge computational matrices in the test time. So we design a relaxation to the loss function, which is shown in equation number 8. So in this, there are techniques in the literature to compute A cross SP faster. So these are called bilateral filtering based approaches to multiply A cross SP in a speedy manner. So overall, this will equation number 8 will be our loss function, and we calculate the gradient of L of S with respect to SP, and dou of L of S by dou of SP is shown in the figure in the equation number 9. This is used to backpropagate the gradients into network layers. Based on this loss function, we propose two different variations referred as small sample and small domain. So small sample refers to sample level adaptation. So we adapt the model for each sample, and when we come across different sample, we reset the model again. So basically for every model, we are trying to adapt and reset the model after the sample is gone in the data stream. So for example, given an image XT, so on the batch size B, we perform different augmentations. Basically B minus 1 data augmentations to XT. So during forward pass, the generated batch of images is passed into the network and the loss is back propagated. And we do multiple forward pass and backward pass. So we set a termination criteria that based on the loss function, if loss between two consecutive iterations is less than a threshold, we will stop the forward and backward passes, and we'll save the segmentation predictions, and we will revert back the model weights to initial model parameters. So the advantage of performing a sample level adaptation is that we do not suffer the performance degradation on daytime images, which is the source domain in this scenario, because the model is restored after every adaptation, we do not lose the performance on the source domain, which is the daytime images. Coming to mall domain, so we're trying to adapt the model to entire domain instead of a single sample. So in mall domain, a pre-trained model is adapted to entire unseen target domain directly during inference. So in mall domain, the changes from mall sample are that we do not revert back the weights of the network parameters, and there are no augmentations of the input image. So basically, the mall domain has advantage of adapting to unseen adverse weather images, let's say rainy night images, directly during inference. But the problem is that we will degrade the source domain performance in this scenario, because the model keeps on updating and it forgets the daytime or source images. So the performance on source, which is daytime, will be decreased. So that is the advantage of mall domain and mall sample. So coming to the experiment setup, we conduct experiments in two settings where the model has seen the target images. That is the second setting, where the model has not seen the target images during training. So in the first setting, we have state-of-the-art daytime models, which are trained on daytime images. And we have domain generalization models. In the second setting, we have unsupervised domain adaptation methods. So coming to the experiments, we conduct extensive experiments on 13 different subset of datasets. ND refers to nighttime driving, DZ refers to dark Zurich, FDD refers to foggy driving, foggy Zurich, and we have different weathers like fog, rain, snow, night, cloud, rain, snow, and overcast condition. So in this table, we compare our performance with 10. So we can observe that across multiple different datasets, the proposed approach performs better than 10. In this nighttime driving, we can observe that it is 33.3 MIOU score, whereas our proposed approach can reach up to 38.4 in terms of MIOU performance on Deep Lab v3 plus mobile net. So since this gives the flexibility of adapting it to different models, we conduct experiments on multiple models like Deep Lab v3 plus ResNet 101 and RefineNet. So in almost all the settings, the current proposed approach outperforms 10. So coming to the experiments on state-of-the-art daytime models. In this setting, we take all the state-of-the-art methods which are proposed in recent years for the task of urban scene segmentation, like BiceNet v2, which is from IJCV 2021, ISANet, which is from IJCV 21, STDC from CUPR 21. So for all these different state-of-the-art methods which are trained on daytime condition, we can observe that, for example, if we consider MobileNet v2, the nighttime driving performance is very poor, like 9.7. So for real world applications, it's not feasible with such lower number, because the goal is to perform well in all the weather conditions, not just daytime conditions. So with our proposed approach, you can see that 9.7 is improved to 33.8. And similar results can be observed in dark Zurich as well. 3.9 MIU is improved to 20.3. So for all these 13 different data sets, we can observe the performance improvement. So qualitative results for input image, we can see in the B, the pre-trained models performance. With our proposed approach, since it can be applied on any pre-trained model, we conduct experiments with Deep Lab v3 plus MobileNet and ResNet 101. So in this, we can observe that the edge corresponding to the footpath is completely missing in MobileNet predictions. So we restore this edge in our predictions. Also observe that the traffic lights, which is an important class to make decisions in real world applications, so it's completely missing in the Deep Lab v3 plus MobileNet. So by enforcing this edge consistency loss, we restore the traffic light class in the predictions. And We can observe that here as well, the traffic lights is restored, which is not present in the actual model predictions. Similarly, for deep lab with replace ResNet 101, the footpath class is completely missing in the actual prediction. So we, by this loss function, we can restore this footpath class, and the noise is also reduced in the blue color, which is shown in the, which is the car class. So the noise is reduced with the loss function as well. So coming to the experiments on state-of-the-art domain generalization models, IBNet, switchable whitening, robustnet are the three proposed approaches in the domain generalization for segmentation literature. So we perform all these experiments on these three models. So we have shown the average improvements across all these 13 different data sets. We can observe that the 39.6 is improved to 41.3, and 34.1 is improved to 37.9. Similar for robustnet, we see that almost around 10% improvement on the average MOU performance. So coming to the qualitative results, we show the results of robustnet R50 and robustnet R101. In the above case, in the snow setting, we can observe that there is a noise with respect to the car setting, and current proposed approach completely restores this traffic lights as well. So thereby it improves the performance in the snow setting. In the fog setting, we can observe that the two signboards which are present are one of the signboard is completely missing in the robustnet R101 predictions, and entire sky is treated as building, because due to foggy conditions there is a problem of visibility. So the model confuses the entire sky as building. So whereas our proposed approach can restore the signboard as well as sky, because the building is being misclassified. So it can be corrected using our proposed framework and improve the performance. Still, there are some scope for improvement. In this case, this is being treated as building, which is not the case in the actual image. So there is scope for improvement in such scenarios. So in the third setting, we conduct the experiments on unsupervised domain adaptation methods. As discussed in unsupervised domain adaptation methods, the model will already saw the unlabeled target images. For example, there are techniques like MGCDA, DANnet, GCMA. These are night-specific segmentation methods, because night is a very complex domain due to glare, shadows, etc. So there are methods which are designed specifically to perform well in nighttime scenario. So even though the proposed method is not focused on improving nighttime setting, we conduct the experiments in night setting as well. So we can observe that there is an improvement of around 1.1% on DANnet, around 0.3%. So 0.3% is not significant enough for night unsupervised domain adaptation methods. But we argue that as a whole, when you see the DANnet performance on adverse weather conditions, the performance can still be improved significantly, around 2%, compared to only 0.3% in dog zodiac setting. So the known limitations of the current work is with respect to inference time. To take the inference time of the proposed tent approach and our approach, we can see that there is around 0.6, around 600 milliseconds. The numbers are shown in milliseconds. For each iteration, how much time the tent takes and mall sample and mall domain takes. For mall sample, we have around 600, which is 0.6 seconds more than the tent. So this is one of the known limitations of the current work. And also updating entire network is time consuming, because the tent only adapts the batch norm layer. The time taken to update the model is considerably faster. So, and updating entire model can be time consuming. That is one of the known limitation. And the similarity between two pixels is considered using a Gaussian 5D kernel based on RGB X5 values. So this is one of the known limitation to maybe come up with a better affinity matrix. So to conclude, the proposed work introduces a novel unsupervised loss function to enforce the edge consistency between the input image and the label predictions. So the goal is to improve the performance in all the weather conditions, such as rain, snow, overcast. Because in these weather conditions, there are not many data sets available in the literature to train the model from the scratch. So it gives a very interesting problem when the data set is smaller, how to adapt the existing models to these different weather and illumination conditions. So it can improve the performance of any existing method because the loss function is designed to only take the predictions of the network. It doesn't depend on the ground truth. So since it can be, for this reason, it can be used with any existing method in the literature. So the experiments are performed on 6 different weather conditions like fog, night, snow, rainy, cloudy, and overcast condition. And it can improve generalization performance on multiple settings like daytime, domain generalization, and unsupervised domain adaptation models. So these are a couple of references from the paper in the presentation. So
I think even the drawback of the time that you pointed out is very generous of you, given the architecture of this paper and model. It's just comparing by 0.6 times 10 is very generous to point out as a drawback. I think that was more of a
yeah, because anyway the reviewers will anyway point it out, right? Because you are saying that your proposed approach is a test time adaptation approach. So what is the time it takes to adapt for each sample? Because if you want to deploy it in real world, and since you are showing the numbers on A100 GPU, in real world you don't have access to the A100 GPUs in deployment. So they will definitely ask this question, especially for test time adaptation method.
That's true. You very well know, I've been trying to deal with a paper which runs out of memory for a batch size of 200 on a A6000 chip. So yeah, the memory and this thing is a constraint. So it was really nice to see that you evaluated the paper on that parameter as well. And yeah, it was like, how much time did it take you, all these data sets, to conduct the experiments?
Yeah, it took a lot of time because to conduct on these multiple data sets, like 13 different data sets. So it took like, so basically what we did is that we have something OpenMM labs, you're aware of that, right? There is like OpenMM segmentation. So we wrote a script which can automatically take any data sets, any model available in MM segmentation. So that gave us the advantage because you can automate the scripts. There are pre-trained models which are existing in MM segmentation. So basically you have to write a bash script to automate this process. So that's why the time, still it takes a lot of time to do experiments on all these data sets. It took almost 3-4 months to conduct experiments.
Interesting. And is the code open source?
Yeah, the code is open source. Yeah, we are in the website we have the mall IITD. We have .github.io. In the paper we have shown again the link.
Nice. Yeah, this looks super good to me. Now I know where you've been busy with all the work. So I don't think there are more questions, and you being the person who used to ask the most number of questions at CVT. One last question that I have is, how did you get the mathematical intuition of modifying the eigenvalue approximation?
So actually, my supervisor used to work in this graph cut related. He has given me a couple of pointers with papers in this space. So that gave me idea to come up with this loss function. So he has given me a couple of pointers to papers to read. So from that papers to come across this.
Interesting. Very interesting. Nice. And all those papers would be in the references, I believe.
Yeah, all those papers are in references.
So it was super nice hosting you, host your own paper, Nikhil. And yeah, if anyone has kept up with us till the end of the talk, we're going to be more regular. We have extremely nice papers lined up. And please feel free to mail us if there's a topic that interests you so that we can bring more talks around that. And yeah, thanks for joining.
Thank you. Thanks, everyone.